Welcome to the amazing world of optical illusions.
So one of the ways that we can tell which eye is our dominant eye is by looking through a piece of paper. So if you close one eye and the image stays the same, and if you close the other eye, it shifts, that means the one that it doesn't shift is your dominant eye.
Okay, for the next part of the lab, we wanted to determine our field of view, both for a monocular and binocular. So to do this, one of us stood over here and walked off to the side. We kept walking off to the side until the observer could no longer see the person walking off to the side. We then counted the tile blocks and determined the angle using trigonometry. Still see you? I can still see you. Wait, I can't see you anymore.
So next we wanted to test where our blind spot was, and the way we did this is we looked at this two spots and closed one of our eyes, and we moved it closer to our face until we couldn't see one of the spots anymore, and that's our blind spot. And the reason for this is because we have the optic nerve in our eye, and it sends messages to our brain, obviously, that we're seeing something. In this spot, we don't have any light receptors, so when the light from the spot falls on the optic nerve, we don't see anything, and that's why we have a blind spot. Next, we took a look at visual acuity, which is the ability for the human eye to see fine detail. This is a model of the human eye and the way objects are projected. The projection of the object is given by this equation, where f is the focal length of the eye and alpha is the subtended visual angle. However, as you can see, there are some limitations to this that depend on Rayleigh's criteria, the pupil size, aberrations, and that is what affects our vision. We did some tests to see what each of our acuity was, and we will show what some of the tests were.
So Edgar's standing 20 feet away, and he's going to perform the visual acuity test right here. So I'm going to ask Edgar to read this line right here.
L-E-F-O-D-P-C-T.
Good job, Edgar! So Edgar just read us line number 9. Let's see if he can do line number 10.
F-D-P-L-T-C-E-O.
Yeah.
Alright, so this is the flicker fusion frequency test. We have a green LED here that's flickering on and off because we have an AC current coming into the green LED, turning it on and off. As we increase the frequency, we see it start to blink faster and faster until you can no longer tell that it's flickering. And at this cutoff rate, we see this cutoff rate because the human eye is no longer able to determine that flickering when the input frequency becomes high enough. Here we're using a green LED because the human eye is most sensitive to the color green. So we're going to see a higher flicker rate for a green LED than we might for a red LED, like that one, or a blue LED.
Here is an example of trying to determine the contrast.
Okay.
For the next part of the lab, we were looking at these stereograms. And what I do is I cross my eyes and look at it. I can see like some jelly bean or something. So I don't know what it is supposed to be. But they don't have the picture of what this is supposed to be.
So for this part of the lab, we used a monochromator, and we can see the cycle through the different colors using a tungsten lamp source. And we use it to see how short wavelengths and how long our eye can distinguish